Anyway, I'll finish the sentence. So what's the problem with this gradient descent idea? It turns out if you're going down a narrow valley, I don't know if you can sort of imagine a narrow valley toward the bottom. So here's the bottom. Here's your starting point. And this is, so you have to think of this as a bowl. So the bowl is, or the two eigenvalues, you could say, are 1 and a very small number. The bowl is long and thin. Are you with me? Imagine a long, thin bowl. Then what happens for that case? You take steepest descent, but you cross the valley, and very soon you're climbing again. So you take very small steps, just staggering back and forth across this and getting slowly, but too slowly, toward the bottom. So that's why things have got to be improved. You can't, if you have eigenvalue, a very small eigenvalue and a very large eigenvalue, those tell you the shape of the bowl, of course, and many cases will be like that, have a small and a large eigenvalue, and then you're spending all your time, you're quickly going up the other side, down, up, down, up, down, and you need a new idea. Okay, so that's really, so this is one major reason why positive definite is so important, because positive definite gives pictures like that. But then we have this question of, are the eigenvalues sort of the same size? Of course, if the eigenvalues are all equal, what's my bowl like? Suppose I have the identity. So that x squared plus y squared is my function. Then it's a perfectly circular bowl. What will happen if can you imagine a perfectly circular, like any bowl in the kitchen is probably most likely circular. And suppose I do gradient descent there. I start at some point on this perfectly circular bowl. I start down, and where do I stop in that case? Do I hit bottom? I do. By symmetry, I'm going to, so if I take x squared plus y squared as my function, and I start somewhere, I figure out the gradient. Yeah, the answer is I'll go right through the center. So really it's positive eigenvalues, positive definite matrices give us a bowl. But if the eigenvalues are far apart, that's when we have problems. Okay. I'm going back to my job, which is this stuff.